Right, so this is lecture 11 on wastewater treatment plants and design. Again, just to confirm, this class will be part of the finals. So everything we cover from now on will not be part of the midterms, which is on week 7, as you see over here. Um, Hold on, let me see, the key's not working. Seems like the Bluetooth is not working, so I'm just going to turn it on. Pencil, see if it is connected. No. Okay. Right. So now this will work. Right. So the midterms is next week. Okay. Next week, which will be on Wednesday. So you'll have some time to prepare for the questions on everything that we cover as well as homework. So we have more than a week to discuss those questions. But the quiz will be on Thursday this week. So I'll release on not Wednesday because Wednesday is a holiday. I'll release on Thursday, and you'll have 20 minutes time to answer the quiz. And again, this will be also 24 hours durations. So one thing I want to mention, homework 4 is due. Actually, this is due today. Today, let me think of this. This is what homework. Oh no, you're right. Homework due is on Friday. I'm sorry, I could not think of clearly. What is that? Homework 5 is released last week. So this was due today. Okay, this is not because I extended until Monday midnight. So anybody who has not submitted, they have time to submit on by tonight. But homework 5, which is released on Thursday, this is a key announcement. There will be no more extension on Friday, if you ask me. The reason is because homework 5 is part of the midterms. I'll release the homework as soon as it's due, the solution. So if you submit after that, it's not going to be graded. The reason is we already gave you the solutions. And just to ensure that this usually I give extension without any question asked. If somebody asks those for extension, just be mindful for this homework. Start today. If you have not started, you got to submit by Friday, which is more than a week because we release on Thursday. And again, the reason we are doing it is because I want to make sure that all the students have the solution for homework 5 available as soon as it's due, so that you can start working on your midterms preparations. So again, don't ask for extension after Friday because it doesn't mean anything because I release the solution at midnight Friday. So start working from now if you have question on homework 5. Again, those are should be easy questions because we have so many examples solved in the class. So if you try from now, you should be able to finish that. Quiz 2, that's based on the week 2 and week 3 and 4. Everything that is on week 3 and 4. That's lecture 5 to 8. Again, this will be 20-minute durations. Will be released on Thursday. The reason I decide to release on Thursday, not earlier, is because I wanted to have an office hour before that, so that you have opportunity to ask me any questions during that office hour. And you can always ask questions before that on CampusWare, which will be always there, just in case because there is no class on Wednesday. I wanted to make sure that you have at least one more opportunity to see me before you um, start working on your quiz. Again, this is 20 minutes durations. So unless you ask for extra time for based on CAE, um, that 20 minutes duration is active until its deadline. So its deadlines whenever it's released, 24 hours from that time. So you got to work 20 minutes before the deadlines for you to able to use that extra 20 entire 20 minutes. Again, office hour on Thursday, which is after the holiday, Wednesday holiday. So that means you should attend the office hour. Just ask any questions related to quiz, any question that you have. Again, I would not wait until that and ask on CampusWare. reading materials, section 5, section 5 on like chapter 6 is what we are going to cover in wastewater treatments. So this is all about wastewater treatment. And as you learn, there is a very minimum concept here on wastewater treatments. Everything else you already learned. We are just going to apply for mass balance to solve those problems today.
Professor, quick question.
Yeah.
For this quiz, are we gonna have a practice quiz like the last one?
No, because I gave you questions on
On the spot.
every lectures always. So every lecture has some quiz questions. But if you have very specific questions on any slide, you can ask those because those will be similar to what we did last time.
Got
And
it. Thank you.
another thing I would suggest is every time you see an equations, just pause for a moment and see what if you understand that conceptually or not. Because a lot of times the questions are all based on the equations, and it's a conceptual question. So either increase, decrease, yes or no type. So I would always emphasize on those for concept.
Got it.
Um,
Thank you.
Let me see if any questions on chat window. Somebody asked why there is no class on Wednesday. It's a Veteran Day holiday, or let me see. Yeah, it's a Veteran Day holiday. There is no class on Wednesday. Although I can release a 2-hour video, but I don't want to. I can release some extra questions and answers from last year homework or homework or midterm solutions. That way you can see those. That may be helpful, but it will not be live class. Okay. All right. So the learning objective, everything we learn today is related to wastewater treatments. And just to reiterate, the most important part of wastewater treatment plant is secondary treatment design, where you remove BOD or organic chemicals by using microorganisms. The concept behind it, everything else is already known. The mass balance, everything else is known. So you'll just apply the concept you already learned to design the wastewater treatment plant. So there is nothing new here now, but you will see how to apply the same concept. If there is a new terms, I'm going to emphasize those so that you know the concept of those specific term. So these are the different objectives. I strongly suggest there is a 10-minute video of how wastewater treatment plants works, and you should watch this one so to get an idea of the concept. But what I'm going to show is I'm going to show another small 3-minute version of the window that will give you more um, specific example of how wastewater treatment plant works. Just to give an idea, so here you are not looking at wastewater coming from industry. We are looking for domestic wastewater. Domestic means now uh, like people's your swear, that doesn't have lots of toxic chemicals. This is just organic from kitchen sink, your restrooms, all those water goes to wastewater treatment plant. So just to clear emphasize there. So let's watch a 3-minute video so that you can see how it works before we go individual concept. So I'm going to see if that works.
Cities and towns have sewerage systems in place to carry the wastewater from our homes, hotels, factories, and other establishments to a sewerage treatment plant where the wastewater is treated. It is then deemed safe to release into other water sources. The treatment of wastewater goes through different stages. Wastewater is treated to remove the physical, chemical, and biological contaminants present in it through various processes. The pre-treatment process involves the sewage being sent through grids or vertical bars that can remove large solid substances like metal cans, paper, and plastic materials. In primary treatment process, the sewage flows through the grit chamber very slowly, so that the sand, pebbles, and soil settle down at the bottom. The sewage flows into the settling tank or sedimentation tank, where the solid wastes like feces are allowed to settle down. Wastes such as soaps, oils, and grease rise to the top of the wastewater. The waste material that settles down at the bottom is called the sludge, and the floatable material is called the scum. Scum is then removed using a skimmer, and sludge is removed with a scraper every few days. The water that is left out is called the clarified water. In the secondary treatment process, biological or organic wastes are removed. It is a biological process. This is done by transferring the clarified water into an aeration tank, where air blowers bubble air, which helps the aerobic bacteria to grow and feed on the organic contaminants, such as food waste, feces, and other organisms. The mixture then flows from the aeration tank into the clarifier, where activated sludge settles out by gravity. The activated sludge so produced, along with the sludge produced in the primary process, is transferred to the digester, where it is decomposed by anaerobic bacteria. Biogas is produced in this process, which can be used as fuel or can be used to produce electricity. The activated sludge is then left in the sand drying beds. Some quantity of water in the activated sludge evaporates, and the remaining quantity drains through the sand beds. This leaves behind the remaining dried sludge, which can be used for making fertilizers or compost. In the tertiary treatment process, the leftover wastewater is treated with chlorine to remove the phosphorus compounds, nitrogen compounds, and bacteria. It is a chemical process. Chlorine tablets are added to kill the germs. This process is called chlorination. Then this water is let off into the water bodies.
All right, so what you hear right now was just a basic overview of how wastewater treatment plants works, but specific design or the very specific part of different units are different for different wastewater treatment plants. For instance, it says it's a biological process, but there are many wastewater treatment plants which is anaerobic, where you don't have these aerobic reators. And then the disinfection is not just chlorine; it could have a lot of other factors. For instance, many of the wastewater treatment plants do not remove nitrates or nitrogen or phosphorus compound. So you need to have another filters or another processes. So everything is not described in that one video. It just give you basic overview of most of the common units. Okay. So think of, the wastewaters are sourced from different kind of locations, domestic, industrial, agricultural. But what we are going to discuss today is mostly domestic one. If it is in agriculture, then you have high nitrogen contents, okay, high N and P nutrients content. So you got to remove those more in a different design. But if you have industrial, then it has a very specific type of pollutant. So it might be very specific type of units. So that's why you have to be mindful about which wastewater you are going to treat, and what they have, and what's your main design goal. And so this table 6, that gives you very specific type of contaminants presence. As you see here, you're not looking at very specific pollutants. You're looking for a generic type of pollutant like BOD, COD. That's like basic description of how much organic in your water. And just to let you know, 99.9% of waste water is water. Okay, so by far majority of the, by weight if you calculate, 99.9% is water. So, and but the rest of the 0.1% is all the stuff that you're talking about. That's based on the mass. So that means the majority of the source that you're looking for resource is water. This wastewater can be reused as a drinking water. For instance, if you think of Orange County, they are injecting wastewater into grounds, and that way the grounds, when they inject all that, it will filter out all the any residual pollutants. Then it will again put it back as a drinking waters and treat them before they reuse again. So many big cities were going to reuse wastewater as a drinking waters by different technology. And but mostly what you are looking for is this type of pollutants, because those majority of these pollutants determine what kind of treatment units you should have. This is just to give you a range, because last time I just show you the range here. This is just to show the medium concentration, strong, or all that factors. And as I said, there are lots of non-conventional pollutants. We don't write it there. For example, here many wastewater treatment plants, they actually monitor for pollutants, because if they are releasing into surface water, there is TMDL, or total maximum daily load, associated with that. So they want to make sure they are not releasing the high amount of specific pollutant. So they do monitor all these pollutants. But just to give an idea, wastewater treatment plants are not designed to remove very specific pollutant. If you have a specific concern, they have to add that specific units before they discharge it. That's why I say, there is always a treatment goal that's based on this particular act, a National Pollutant Discharge Elimination Systems, NPDES permit. Every wastewater treatment plant has that permit, because they are discharging this wastewater to a surface water source. For instance, in LA, we discharge most of the wastewater to ocean. So there is a concentration limit, what pollutant concentration you need to have before you have to discharge. So they do monitor those, and these are the typical concentration that treatment goals. BOD 5 should be less than 30 milligram per liters, and so all the other things are given. All right, so that's the treatment goal. Now let's get back to the specific different design units. Again, what you saw in that video, these are all the stuffs that's written here. You start with raw sewage, and then you have some kind of pre-treatments to remove the large particles. For instance, plastic trash, all these big trash, you want to remove them before it goes to the actual treatment. So these pre-treatments are mostly filtration based and sedimentation based. So you see bar rack, that's basically bars at spacing, whatever the spacing they need, and they remove all those larger particles. Grid chamber, again, as you see, those are going to settle all the large sand or sediments. Then equalization basin, basically everything else, they have to crush into smaller particles. That way it can be effectively removed in the second steps. Um, then you have primary settling. Primary settling, as you see over here, um, those are uh, those are very much. Let me put this one. Those are you already learned. Primary treatment is basically a sedimentation tank. The circular, big, big circular tank that you see in wastewater treatments, those are actually primary treatment units, where water moves slowly and then overflow, and that's how you settle all the particulates. And so those primary treatments can remove 35% of BOD. When we say BOD, it could be not just dissolve, it could be also particulates, because there are debris which is organic. So that's why it does. They can also remove some of those dissolved substance along with the coagulations or settling. Um, then the most important part here, what we are going to discuss, is secondary treatments, where you remove those 85% of the BOD um, by using bacteria. So this is a biological treatment system. Okay, and again, this is aerobic. Doesn't mean that every wastewater treatment plants is aerobic. By far, the maximum wastewater treatment plants are aerobic, and this is also the most expensive unit. and the most expense comes from pumping air, because you need air for microorganisms to breathe oxygen and degrade those food. There are other treatment units where you have anaerobic treatments, entire anaerobic, where you you remove organic pollutants by digesting them in anaerobic environments where there is no oxygen. So you'll produce methane. And for anaerobic treatments to be effective, your water has to have lots of organic. Okay, so that's why you might have heard about some wastewater treatment plants where they actually take the waste food. So all the waste food from restaurants, they take it and dump inside the wastewater because they want to increase that amount of organic for anaerobic treatment to be effective. So we'll discuss that in next few classes. But today we are going to discuss secondary treatments. And then the advanced or tertiary treatments is more about disinfections. Okay. So now that you learned the process, let's identify different removal processes. So if I ask you, what are the removal processes in this pre-treatments, what you would write? Any volunteers? Think of what they remove in the bar rack. What kind of stuff you'll remove in that bar rack?
Large trash, paper,
So what,
cans,
yes,
bottles.
exactly. So what process it would be? What do you call that?
It would be filtration, wouldn't it?
Exactly. It's a filtrations. Because filtration is basically, the size dependent process. If you have a strain, you remove all that. Grit chamber. What kind of process in grit chamber?
It'd be like a sedimentation, settling type thing.
Exactly. So sedimentations. Equalizer basin, it doesn't have, really, it doesn't remove that. It just makes it uniform. Primary settling. This is as clear. You already mentioned sedimentations. That's the. You have also some extent if you have. They don't usually don't have coagulations or fluctuations in wastewater because those are usually designed for drinking water. But sometimes you might see those, but it's not very common. So I'm not going to write that there. The secondary treatments is already written there. So this is already written. It's a biological process. Biologicals, but I'm just going to emphasize this one. This is aerobic. Okay, that means you have carbon, which is the substrate, and you add oxygens. You have microorganism that becomes CO2. Okay, and also more microorganism because plus energy. So this is BOD. Okay. Um, so that's why you have to pump lots of oxygen. So this is most energy intensive unit. Energy intensive unit. And there are advantages, there are disadvantages. So for instance, if you want to make it anaerobic, so some treatments, it's not written here, but if you make anaerobic, what you do is you produce methane. Okay. So that's now this is energy. You can extract energy. So that means anaerobic process is energy positive process where you do get energy, you don't spend energy. So in fact, a lot of times they do have combination of both, where they have some anaerobic units which produce energy that will be fed to the aeration chambers. But then you might ask, why people are not using anaerobic all the time. Well, as you see, this is more efficient if you have lots of carbon, and typically wastewater doesn't have that much BOD to make it efficient. So that means lots of wastewater treatment plants actually receive food waste to increase their carbon concentrations to make it high enough to be sustainable for anaerobic design. And so that means anaerobic wastewater treatment plants will be mostly common in a big cities where you have constant supply of high quality food waste or the organic source. Any questions on this? All right, so let's see a quiz, because this is a multiple quiz question here. So what you have to do is tell me, I gave you pollutants here, and you have to identify which location that will be removed. So I'm just going to label it 1, 2, 3, 4, 5, 6. So you got to tell me where those pollutants are removed. So number one, large debris and plastic. In this picture, which one will remove that?
There is a question in the chat. Actually, I think.
Yeah, identify pollutants that are removed at different section of the. So you have the pollutant. So you got to tell me where in these pictures where those pollutants are removed. Large debris. Can you identify the locations where they are removed?
Iman said the screen and grit chamber.
Yes. So that will be here. Where I'm going to write the 2. I'm going to zoom out. So where should be suspended solids are removed?
Probably primary sedimentation.
Exactly. So that's going to be 2. Then BOD. BOD is organic contaminants, right? So those are mostly dissolved.
Bioreactor.
Exactly. So that's BOD is, as I said, C plus O2, CO2. So that will be here. Where the biomass is produced or removed. So bioreactor is basically you are removing BOD by creating microorganism, because some of the organic become carbon dioxide and energy, some rest of them they're assimilated in their body to become more biomass. So you have to remove those bacteria before you discharge it. So that biomass will be removed here. Okay. So the difference between 2 and 4 is that 2 remove most of the particulates that's in the wastewater. The secondary sedimentation, they remove all the microorganisms created in 3. Okay. So you don't have lots of microorganisms.
I have a question. The biomass, would that also be removed through the sludge processing?
Yes. So in fact, that's why the sludge processing create the fertilizer, and in fact, those fertilizers are the bacteria. They are basically dead biomass, so they have lots of nutrients and all that. Okay, and so we call that, sometimes they call suspended, volatile suspended solid. The reason they call volatile suspended, so I'm going to write here volatile suspended solid, which is volatile suspended solid, and this one is suspended solid. Okay, there's a big difference. The difference is volatile. That means, if you burn them at high temperature, 500 degrees Celsius maximum, you can remove those solid from the sludge. So think of leaves are volatile suspended solid in that definition, because you can, if you burn them, you'll have nothing. Whereas if you take a sand, you burn them at 500 degrees Celsius, nothing will happen. So that's how they distinguish with how much fraction is actually bacteria, by just burning them, burning the solid. So those volatile suspended solid will give them some idea about how much biomass is produced in 3 of the bioreactors. So that's a clear distinction between the 2 different sedimentation process. And some of those biomass is again put it back in your influence. The reason is this bioreactor is more efficient. You have lots of bacteria, and naturally wastewater doesn't have a lot of bacteria, so they have to add always to make it more efficient. And then some of the sludge are treated, and then they are for disposal. Then we'll discuss about that. Again, these bioreactors, as you see, has multiple definitions. They write aeration basin, which is very common, where you have add oxygen, or it could be membrane bioreactors, where you don't have adding oxygen, but what you are doing is you have a membrane that is moving. So that means the bacteria is settled on the membrane surface. That way you don't have to have lots of bacteria suspended in the system. There could be also trickling filters. Means you have large sand filters or not sand, gravel, and bacteria are growing on the surface of the gravel. That way, as the water moves through it, the bacteria is removing those organics. So these are the process is very similar. The difference is where the bacteria are they suspended or they are attached to something else. And then lastly, you have disinfection process here. So that's where it remove pathogens, number 5. Okay. Um, and waste solids are basically here, number 6. So now again, same question, why you are using disinfection at the end, not at the beginning, is because if you use at the beginning, you'll kill the bacteria that you need for bioreactors. And also you'll have to destroy so much, it's not efficient because you'll have so much other stuffs that is there to decrease the disinfection process. So you'll never have disinfectant or disinfections at the beginning, at the end, because you want to protect those microorganisms as well as it's not efficient. But if you replace all of that by let's say RO, reverse osmosis, of course you have to put the disinfection before that because you don't want the membrane to clog. So we'll learn about membrane in next class, but today we are mostly on this process. Again, I show you this particular video before, so this should all we are going to discuss that is based on that video, or at least we already discussed that. So quickly, bare racks, how they look like. Look how they look like here. So basically, you have these rods and they're moving, breathe chambers. So first, anything smaller than that particles will be removed. Everything bigger than that particles either removed or crossed to smaller particles before it goes there. So this is a more like a equalizer with mechanically crushing chambers. Before that, there is a bar rack or filters. That's like a basically screen. Grid chamber, as I said, now there are different design based on how you settle the sand or particulates. So the way water moves will affect the settling of the tank. So for instance, at the bottom, if you see how it goes, you have inlets here, and then water moves like a spiral motions. Okay, so that spiral motions always helps um, clean, always helps removing the particulates. Okay, and so there is a driver units, and then there you have also another system on the top where it force the water to move in helical directions. Because of that speed, the particles are like in that path projected out of that circle, so that way it is more efficient to remove those particulates. So and again, the difference between this and the settling tank is your fluid motion is not linear. It's like it has to have some kind of spiral motion, which that way you can force out the large particulates from the system. So primary treatment systems is again we already covered so extensively. They look like this. They are slowly water moves from one area and then overflow on the top, and everything that's going to settle at the bottom. We know the again settling velocity. We know this one, so that's let me see if I remember. I know this is the difference between particles velocity or solid velocity minus wall, and then you have viscosity, and then you have also particle size square, and then there is a terms here. There is a constant here, 8 somewhere. I have to check. So I'm just going to write it here. So this equation is not, there is a g terms, acceleration due to gravity. I think there is a 18 or something. I have to check somewhere. Just check this one. But point is that this primary settling tanks depends on the difference in particles density as well as particle size. The bigger the particle size, more easy to settle. The more heavier the particles is going to settle. Viscosity doesn't change much, so you not have to think of that effectively. But viscosity can change if it is winter to summer, so that means you have some degree of inefficiency there. We learned that one many times, so I'm just going to just give examples. This is also part of your homework 5, you as you see. So I'm just going to give another example here to just give you the concept. So most of the questions in homeworks are related to the design or the size are given. You are calculating the removal percentage. But in these questions, in the examples, what they do is they do it opposite. They say the removal, they give you everything. The only thing they didn't give you the size. So you have to back calculate the size. So let's see the how to solve it. So town of 30,000 people sends half cubic meters of wastewater per person per day to the wastewater treatment plant. A conventional circular primary clarifier. So it's a circular. That means you can determine the diameters. Um, Clarifier would be designed to have an average retention time of 2 hours. So average retention time means this is the retention time, okay? That's the time it takes, the average amount of times water stays inside the system. So that's basically volume of volume divided by flow rate. Okay, how much flow rate you are adding. So this is volume of clarifier. An average overflow rate. Overflow rate is basically velocity of overflow rate. So this is 2 hours. Is 40 meters per day. Overflow rate again is if you remember what is overflow rate, that's basically flow rate. This is flow. Which is this meter cube per day. Flow rate divided by the area, this area, because overflow is happening in that area, not the side area. So that divided by AB. So now question is, where the high rate clarifier would have an average overflow rate of this one. So it says high rate clarifier, you have to have high overflow rate. That's only the difference. What would be the dimension of the conventional clarifier? So I ask you what is the dimension, means you have to determine dB and you have to determine diameters as well as the depth. So let's think of how to determine. So the dimensions are not given, but it is given throughout the system if you see where it is. So let's see. Any questions? Let me see chat window. Yeah, theta is retention time. Okay, so retention. Okay, so think of these equations, overflow rate. It has some dimension, so you might be able to calculate that, because if you know AB, you'll be able to calculate diameters. So what is AB then? Q by overflow rate. Q is 5 meter cube. Overflow rate is Q is meter cube per day. So that's another way to remember. This is 440 meter per day. So that will give you the area of that one. So that will be 5 divided by 40. So which will be, let me see. Let me calculate in Excel. Anybody has a calculator? Otherwise, I'm just going to do that.
You have to
0.125.
How much you say?
0.125.
0.125. Thank you.
Professor,
Yeah.
isn't the flow rate 0.5?
Oh, you're right. I'm sorry. Then this number should change then.
Don't you have to multiply by 30,000 as well?
Okay, I'm completely wrong now. Thank you all. So I didn't even pay attention to what they wrote. A town of 30 meters, 3,000 cents, 0.5 meter cube of wastewater per person per day. So it says this much volume. So I didn't even think of for 0.5 meter cube. It's a so small number. So this much volume is generated by a person, and you are 30,000 people sending 0.5. So you're right. So let's calculate this Q first. 0.5 meter cube per person times 30,000 per person per day, then 30,000 persons. So that would be 0.5 times 30,000. 5 times 3 is 15. So if I take another 0 out to account for that, so that will be 30,000. So that will be 30. So that's meter cube per day. Okay, so that changed it, everything. So thank you all. This has been erroneous day. So I'm just going to erase all that. So let's redo again. So 15,000 meter cube per day divided by well, the overflow rate is 40 meter per day. So that would give you some high number. 10 out. So 12, so that will be
375 meters squared.
Okay, thank you. So if you know the area, this is a circular area. So that means pi dB square by 4 is 375 meter square or square meters. So dB or dB would be 4 times 375. Let me not make it messy. 375 divided by pi square root. Okay, so that will be in meter. Okay, so that's how you determine D. Now, how do you determine dB? dB you can determine based on that because dB is related to volume, and that equation is here. Okay, so I'm just going to write here theta retention time is flow rate divided by, oh no, not flow rate, volume divided by flow rate. So volume divided by flow rate. Flow rate is Q, and total volume is pi dP square by 4 times the height. That's a cylinder, so that's the height is dB by flow rate. Okay, so that means you can calculate dB would be flow rate times theta divided by this is 4 pi dB square. And one thing you have to be mindful, theta is in hour. Okay, so you have to change to convert into unit. So this is a meter cube per day. This is hour. So that means you have to change one day would be how many hours? 24 hour. Okay, so that you have this similar unit. Everything else should be okay. So this meter square, so this is meter cube, so this answer should be in meter. Okay, so a lot of times your questions in midterms will be like indirect like this because you have given everything, you just have to back calculate all of that. So I would always pay attention to the process in your homework questions because midterm questions will be exactly similar, but the type of information given to you will be maybe opposite. So you have to back calculate a lot of these factors like that. Okay. Any questions?
Can you go to slide 18?
Okay.
Yeah, like you got right there, you got dB.
Okay.
That's right. And then like on the next slide, did you like integrate the equation or?
No, you don't have to integrate because it's already given. So dB is given.
Oh, okay.
Okay, so you just substitute that value directly. Because you are just rearranging. I'm just trying to find what is the capital dB is. This is already you calculated.
And
Calculated.
we calculated on the slide 18. Okay.
Yes. Okay. And the second question is how much area would be saved by using high rate clarifier. So this one is basically saying what that AB would be if you use high rate clarifier. So we always use 40, right? That's the one we calculated. So if you think of overflow rate, if you use high rate average overflow rate of 15 meter cube per day, so if overflow rate is 15,000 or 15, let's see what it's saying, 1500 meter per day. So that's the overflow rate. That means you know that overflow rate is Q over area. Okay, you already know the area. They're saying how much area is going to be. So that means your area would be new area would be Q over V. So that's we know this one is 1500 meter cube or 15,000 meter cube per day divided. This is 1500. So that means you are looking for 10 meter square. Okay. So that's the area. So that means you have to check what's your initial other area was. Your area was 375 meter square before. Now you reduce that to 10 meter square. So you do reduce significantly. If you are, that's the correct answers. Yeah, that's how it should be able to calculate. Okay, so again, these are all things you already know. So you learn a little bit more about the specific part of the treatment design, but the most important part of wastewater treatment plants is BOD removal, which is secondary treatments. And so again, you know the concept of BOD. So we're just going to apply BOD and mass balance to solve the example, solve the problem. So this will be very quick not quick in the sense, we'll just go through the background very quickly. Again, the concept here is that you have microorganism which take this carbon from BOD, so that's the source, and you supply O2. This is you supply. Then the idea is they produce carbon dioxide, which will go to atmosphere, and then you don't have to, because that's not complete removal of carbons. And then what you got is basically lots of microorganisms because they are growing inside. Okay, so there will be much more microorganisms. So I'm going to put that downward arrow just to show that they are creating lots of solid. Okay, so which wastewater treatment plants are more efficient? Any wastewater treatment plants where microorganism can produce carbon dioxide more efficiently are more likely to the efficient wastewater treatment plant. Because you don't want to you don't want to create lots of microorganisms. You want the microorganisms to eat the carbon and produce carbon dioxide and not grow that much. Because if it grows so much, you have to deal with all this as a bio waste. So this is a waste. Okay. So what you are doing here is you are creating you are removing one type of waste and creating another type of waste. Whereas this is not supposed to produce waste. So a very efficient wastewater treatment plants are those plants where they remove all the BOD, yet they don't produce lots of this sludge. Okay, so that's what you have to think of. Okay, so when you think of how to design those. So basic ingredients, as I said, you need microorganism. That's number one, because the biological reactors. You need to have a good contact time between organism and wastewater. So this is wastewater. The longer they stay inside the system, the more likely the organism is going to degrade it. Because biological processes are very slow, so that means you need that contact time. then you have to have also lots of waste available, because if you don't have lots of food, they are not going to be efficient. That's why the wastewater treatment quality is also important. If it's pretty clean, it's very hard to make the biological system very efficient. That's why sometimes you have to add some more waste. They add organic. If the quality become very good, they have to add some kind of organic. So they always save some of the very nasty waste around it, just to add them, dump them back into the system. Um, then the third one, which is more on climate or conditions, is temperatures. That's why the wastewater treatment plants are not very efficient in winter. So you have to think of how to heat up those wastewater. pH, if you have microorganisms are more efficient at neutral pH. So the pH has exceed much higher or lower, then there will be a problem. So you have to adjust the pH if it is needed. And it should have also nutrients and other things, because nutrients are critical for bacterial growth. It's not just carbon. So you got to think of all that. And most importantly, it should not have lots of toxic waste, which will kill the microorganism, because it's a biological treatment unit. So that's why everything that we think of here is mostly domestic treatment water. And when you think of biological process, the bacteria can be either dispersed, which is like aeration tank, or it could be fixed growth. Fixed growth means bacteria or microorganism are fixed on on a surface. Okay, and that surface might be moving, just to make it more easier to interactions. So that could be, that's why it says, if you think of peaks growth, trickling filter, that's basically a gravel where all the wastewater is dumped on the top slowly, so that as it moves slowly trickle down, it will go through on the surface, and that surface has biofilm. Whereas rotating biological contactor is basically a fan. So it's a big plates moving in the wastewater treatments, which will have bacteria on the surface. So that's why you have more contacts. Okay. So then you don't have to aerate them again, because the bacteria here is moving. So there are advantages, disadvantages of both systems, but just know that they are different types. So again, in the same process, you have there is certain definitions how people write. When you think of RAS, WAS, just think of what that means. Waste activated sludge, basically, which is coming from secondary clarifier, everything that's all the bacteria, the biomass, and they recycle some of them because they want to increase the microbial organism into wastewater treatment plants. Then that's why they add some, they recycle some of the bacteria or microorganism. The remaining amount is called waste activated sludge. Means this will not go anywhere else. They will have to process them and make as a landfill or all the other things. Let's see, waste activated sludge. Okay, so, and some of the waste activated sludge, as you see, this is the way it is written here is kind of confusing. Some of them are also discharged to, hold on, what is this? Discharged to river land applications. This graph is written in a weird ways. What you discharge here is the water, treated water discharged to river. Okay, you don't discharge the sludge to river. But you discharge the some of the waste activated sludge is applied as a fertilizers on land. So just to know this RAS, sometimes you may see these terms in your questions. So that's why I wrote this one here, so that you know what those mean. And when you say mixed liquid, the reason it's called mixed liquid is because you have microorganism as well as the BOD together. That's why it's called mixed liquid. So these terms might be sometimes confusing. So always come back to this slide so that you know what those are. Okay, activated sludge, all that factors. And tertiary treatments, we're not going to go through it. You already know this means disinfections. You write EV disinfection sometimes, but this is more common. Chlorine disinfection is much more common than any other type of disinfections. This is already covered. Again, this is disinfection rate. You know this let's say d concentration by dt equal to minus k concentrations of microorganism. Here this is microorganism, so biomass microorganism, or particularly this is pathogens. We are looking for pathogens, not the other type. So we are not going to cover that. So mostly we are going to cover the design of activated slots. Any question? Okay, so let me see the chat window just in case there are questions. Oh, you're right. So what I wrote, so D, what is D versus D? Okay, this D is diameters. Capital D is the depth. Okay, so all right, so now this is the main part of the wastewater treatment plant design. So let's understand the concept. There are many terms. There are many symbols that you see over here that can be very confusing. Just let's go through notation type. You know what those means. Every time you see Q, that is a flow rate. Okay. Then you have there are multiple things. Now, first, there are the wastewater treatment plants. If you think of wastewater, if you take a wastewater, it has a lot of things. It has microorganism. Okay, so that's we call X. X means microorganism. Okay, and you call that a lot of times we call volatile suspended solid. Again, the reason is you can burn them. You know, the biomass is not solid that you cannot remove, because that's the way they measure what is the sand versus microorganism. That's why they call volatile suspended solid. Okay, and S is food or BOD. Anytime you write S capital S, that's the substrate or food or BOD. So you have two different types of concentrations. One is the substrate which you want to remove. Another is microorganism which you need it to remove the substrate S. And then you have lots of subscript as R, O, E. Okay, when you see E, E means effluent. Okay, means things are being treated. That's the effluents. O are the reason O they write is just basically influence. Okay, it's like if you see the initial concentration 0, they always write. So that's why they write 0 every time you see over here. So this is coming from primary. Okay, this is coming from primary treatment system. So after primary treatments, everything that goes here is the S0. So this S0 is not, just to give you an idea, this is not in original wastewater. The reason is primary treatment system is already removing some of the BOD. So that means you have to account for those factors. So S0 is remaining amount of BOD after the primary treatments. And R is recycle. Okay. Every time you see recycle, that means R. So where the R comes here? Again, as I said, the typical wastewater treatment plant doesn't have lots of microorganisms, so you have to recycle some of those back here. So that's why you see this return sludge, or is recycle or return. So some of those are coming here, so that's why you see this R. Okay. So QR coming in here, Q plus QR, so they add together, that the flow rate become Q plus QR, and then the remaining amount, and some of the sludge come here. So QW is the amount of waste produced. So this is solid waste flow. Even though it's called solid waste, it actually makes liquid. That means it's not really like a completely solid as water, but majority of them are solid. And then the remaining amount, Q minus QW, goes to, this is QR plus QW. Okay. Then Q minus QW goes to outside. So if you think of this is your control volume, because you are combining those secondary treatments as well as the secondary aeration tank as one unit. So this is the entire reactor. Then you don't have to account for the recycling. So you have just one input. So this is one input. This is output one, output two. That way you can do the mass balance more effectively. So it says the question is, does what it says after O and E? O means influent, E means effluent. Okay. R is return or recycle. Is V is the volatile solid. Where is V? No, V is the volume. So this V over here is the volume of reactor. Okay. Any other questions? Because you'll see this figure all the time when you solve the secondary treatment unit. So it's very important to know what these terms are. And when you do the mass balance, this is how you do the mass balance. So think of, if you are doing the mass balance for S, I'm just giving an example here. If you do mass balance for S, what you write here, everything that's coming in should be what is going out. So S0 times Q, that's coming in. What's leaving the system? Q minus QW times S plus, that's here. The second unit is QW times S. Okay, so that's the mass balance for the BOD. If you do mass balance for microorganism, that will be Q times whatever microorganism comes here, that will be 0. Okay, there is no microorganism, or the concentration is so low that is there is no. Let's say for sake of simplicity, I'm going to write X0. So if I write that one, so Q times X0 should be Q minus QW times XC plus QW times XR. Oh, sorry, that's not the. So these are mass balance equations. So you can solve for all that if you know each terms like this. Any questions? And again, this is a steady state. That means you are assuming there is no change in concentration, other terms. So this is the steady state. Steady state. All right. So again, if you do the mass balance for activated slot design, means I'm asking about this one particularly. Okay. Then what would be the mass balance for that one? So if you think what's the flow in coming in, so the in would be Q plus QR. If you think what is coming out, Q plus QR. Recycling is QR. Okay. So that's, you're talking about what's coming on there or not. So now question is, why some of the flow from secondary treatment is recycled? So I wrote this question here just to give you emphasize that because wastewater doesn't have high X. Okay. Usually you don't have lots of microorganisms to initiate the treatment process. So you have to always add some more because you are losing all that in this to make it more efficient. And X is needed for efficiency. If you think of substrate, what is that substrate means? Is basically No, this is not substrate. The way it is written here. Substrate is basically BOD. Okay. There are two things written here. Let me see if there's some. So these
Sir,
are,
we had a question. Is there no reaction factor for the when you do the mass balance?
there is reaction, but that reaction is what makes the S become smallest. So you're not writing those there because that reaction is inside the systems. So you're not writing that. It's just a concentration mass balance. And every reaction is already accounted for part of that S value. But you will see that when you write the final mass balance equation, there is a reaction terms. For instance, this S, when you write that one, there will be a reactions of this C. So wait for the last mass balance equation, which will solve from that particular point. All right, so there are a couple of things, substrates and volatile suspended solid. Okay, so volatile suspended solids are microorganism. Okay, um, so this will be X. Okay, I'm asking for X. So X are microorganisms which are present naturally, but they grow inside those aeration tanks. So some of them you are going to put it back. So they need to grow to increase biomass quantity. So that's why, again, the definitions why volatile is because of this. Volatile means you can burn them between 105 to 500 degrees Celsius. You cannot burn the sand. You cannot burn the clay particles. You can burn the rock. So that's why they are not partly included. They are termed as volatile suspended solid. So one key component here, when they define this thing, they didn't think of plastics and all that factors. Okay. All right. So what is activated flaws design? So let me see why when I put this one. I already discussed this one. All it's saying is what different processes are. So you have aeration tank. All your goal is to add oxygen here, and then CO2 released here, and you produce carbon dioxide as well as microorganism. In this process, you are settling. Okay, so this is velocity of settling, and your goal in the settling tank is remove all the microorganism because you don't want them to be in the wastewater. So here your microorganism grow, here your microorganism removed. Okay, so that's the whole idea here, because that's where the aeration tank, that's where you are treating them. There is no treatments of wastewater in the second unit, in the secondary unit. You are not removing the concentration of S. So that's why you see this S concentration, S0 is very, very higher than S. The reason is you remove most of the uh, BOD in that aeration tank. Once is removed, you don't remove any more S in these units. So that's why you see this concentration doesn't change between here to here after going through this process. So this S is always constant after it goes out of the aeration tank. Whereas here, if you see X value, this X value is very high because you are producing lots of microorganism in the aeration tank. So you remove a lot of these X by settling. So XR would be greater than X, and X would be much greater than XE. Okay. So another way to say is you remove so much microorganism there that the effluent will have very small quantity of XE, just to show the comparisons. Everything else is kind of given. So these are the things you are going to use when you are, so this is going to be discharged to surface water before tertiary treatments, and this will go to the biosolid land application as a fertilizers. Okay. And what we are going to discuss is the different terms that you already know. So I'm going to reintroduce the same terms again. As you know, this biological organism, like one of the question was, what's the reaction term? That reaction term is inside here. So your X is changing, as I said, your X is changing and your S is decreasing. That's what happens inside inside the aeration tank. Okay. Aeration tank, or this is aeration tank. Okay. So that X is changing at certain rate and S is changing also at certain rate. So how do you know that one? So first thing, let's look at the microbial growth rate. So microbial growth rate is how fast the microorganism is growing inside the aeration tank. So dx by dt is a constant. That's the growth mu. That's the growth rate times the amount of microorganism present in the system. So that, as you see, the growth is not necessarily a function of just the microorganism. You also know that growth is a function of how much food they have. So that's why if you measure the growth rate, which is substrate concentration S and growth, you'll get this kind of curve. What that means is if you have very small quantity of food available, initially microorganisms grow much faster because they are competing for the food and they are hungry, they are growing. But as you give more and more food, what will happen? The growth rate will decrease. The reason it decrease after a point is because couple of things. When there are so much microorganism, because they are growing so much, they will also produce lots of toxic waste. So that will slow down the growth rate because they are not going to grow that much. And also amount of food available at that point per microorganism will also decrease. So that means they will not be growing sufficiently. Okay, so that's why the growth rate is much higher initially at low concentration of food. But if you increase the food amount, there will be a lot of waste and other things that will slow down the growth rate. So if you want to know what that means, is the mu is variables. So if mu is variable, how do you include that mu value here? Because I just say that it's a constant, whereas in wastewater treatment plant, S can vary a lot. So how do you write that value? So that's why you have to always write mu coupled with the substrate amount available in the wastewater. So that's why it is written Ks. Again, Ks is half saturation constant. So this is half saturation constant, which is means your F equal to Ks when mu equal to mu m by 2. That means it's like half life is the same as half reaction constant. What that means is the amount of food is needed to increase the growth rate to half of the maximum that can be achievable. And why Ks is important? Ks determines how much sludge you are going to produce. Okay, K is very important because that determine the sludge produced. So now think of this way: you really need a bacteria grow which is very fast. Okay, high growth rate is needed, but how much food they need to grow that much is very important to know how what they will produce. For instance, let's say this is wastewater treatment plants 1, and I'm going to produce another one. Okay, so QM, this is KS2. So what's the difference? What that means is this type of microorganism, even if they have lots of BOD, they don't grow as they they will consume lots of substrate before they reach that half saturation, half rate growth rate constant. Why it is important? That means the difference means their metabolism. Okay, so what they are saying is, think of me, I gain very quickly. So that means if I eat even small quantity of food, I grow very fast. Means I'm growing means mass, the amount of mass I accumulate, which is good for my growth. but that means, I'll produce lots of waste because these microorganisms are becoming your sludge. So you don't want them to grow so much. You want them to grow. You want them to grow at the expense of treating a lot of wastewater, not as a treating a small quantity of wastewater. So that means, if your KS2 is very high, if KS is increasing, your sludge production for treatments will decrease. Okay, so that means you are producing less and less sludge. So that's why it's very important to think of the conceptually why it is important. But in math, when you solve the problem, you don't need to know. This is more like a quiz questions or concept question.
I have a question.
Uh-huh.
What does RG means?
RG is growth rate. This
Okay.
is growth rate. So R means rate and G stands for growth. Okay. I'm just going to write rate here. So makes it easier. Okay, so now, as I said, this KS depends on how much substrate or the BOD they consume before when they grow. So that utilization rate is important to understand how much sludge is being produced. So that's why, the RSU is the sludge utilization rate. So SU, okay. Sludge utilization rate means how much sludge or how much BOD is being used. So that's the DS by DT. Okay, substrate utilization rate. I'm sorry, substrate utilization rate. DS by DT is DS over. So if I break it down, DS over DX by DT, what it means is it will become DX over DT. What does that mean? If this microorganism produced per substrate utilized. Substrate means waste or BOD utilized. Okay. So what you need is a low yield. Okay, you don't want the microorganisms to produce a lot. If they produce a very high amount, you have to deal with this the solid waste. You also don't want Y to be very small. That means, your wastewater treatment plants will take long time to restart because it takes, microorganisms to go to certain amount. So your yield, you want the Y to be not too high because it produces waste. Okay, and it should not be also not too low because that means it's less efficient. Because if there are not enough microorganisms, the entire wastewater treatment plants will not be efficient. So your Y value will be something in between. So just know the concept. So as you know, the maximum growth rate is related to the maximum specific substrate utilization rate. So that K is basically is YM divided by yield. This is just a different terms that you should write those. So every time I ask a question related to what's the substrate utilization rate depends on, this constant. So X, it increase with increase in concentration of X. It decrease with yield. So this increases if this would increase, and it increases if this increase. And when you think of S, it's let's say decrease with KS. But if you are looking at S, then you have to do the ratio. So this depends on KS by S. Okay, because both have similar units, so you have to think of that. So these equations are very important for you to understand conceptually why substrate utilization rate increases with X. X means microorganism. Well, if you have more microorganism, you should utilize more substrate or more food. Why it increase with K? K is the maximum specific substrate utilization rate. And obviously that that one depends on if it is increasing more maximum utilization, obviously your substrate utilization rate should increase. So think of why substrate utilization increases with decreases in yield. What is yield means? Yield means not how much microorganism produced per substrate utilized. If your yield is low, that means you are not producing enough enough microorganism. If you don't have enough microorganism, you are not going to consume lots of organics. So you got to think of all that conceptually so that you should be able to answer those quiz questions in final or the third quiz as well as your final exams. So these concepts are important. Every time you see equations, you should think of conceptually what those means. Obviously, you can just write the equation and able to answers without that. So one thing I want to say that the final concept that you have to think of is death of microorganism. We talk about growth as if those bacteria will not die or the microorganism, but they will die when there is less food. So you have to account for how much they are killed. So that's why it's written, this is death rate means how much microorganism die per unit time. So dx is microorganism, this is microorganism, okay? Organism concentrations or volatile suspended solid. Dx over dt is minus kdx. Again, this negative sign is because decreasing. Okay, the other one is increasing, so there was a positive sign. Okay, there is positive sign because growth means it's increasing, so there is no sign there. Whereas this is negative sign. So the net growth rate would be amount grow minus the amount removed, because the negative term here, so you directly write it there. So growth rate is this, and I already have growth rate somewhere written, this value. This is no minus here, so that's right, minus kdx. So that's the, if somebody asks you what is the net growth rate, if you have to calculate this value, you have the equations. So S is from wastewater. So this is BOD concentrations. Ks, mu m, these are function of microorganism, organism or waste, and these are usually given. Okay, Kd is also given. X values are usually supplied. Okay, so any wastewater treatment plants, these are usually given. Value given. This is a constant. Okay, so these are all constant. So as long as you know this constant, the only variables, so these are variables, you should be able to calculate the growth rate at specific for a wastewater treatment plants. So having said that, what I'm going to do is I'm going to say a couple of concepts this one before I explain how to solve these questions. So these questions I'll solve in the recording or we'll solve in the next class because it's not really needed. We have still another one class for wastewater. So what I'm going to do is I'm going to explain the concept of sludge retention time. Sludge retention time means how much time the sludge or microorganisms stay in the system. As you know, why it is important? Because the longer time the microorganisms stay in the system, they are able to remove or treat contaminants. So if you think of mass balance, sludge retention time is basically volume, the total amount of sludge. So this is the sludge retention time is total sludge by sludge removal rate. So think of retention time, how much time water stays in your bathtub is basically how much water in the bathtub divided by the rate at which you are removing from the bathtub. So exactly same thing. So now let's think of total sludge. Total sludge is basically where the sludge are being produced is in the aeration tank. After that, they are not being produced. Everything is just recycled. So the total amount of sludge is inside the system. So that will be volume times the concentration of sludge. So this is volume. This is concentrations. Okay, so you multiply those together, you get the total amount of sludge produced at any time. Okay, any day. How much sludge is removed from the system? If you think this one is kind of negligible, okay, there is very small quantity of XC. So another way to write is F SRT is, this is B times X. So that's the total amount to produce. You can write Q minus QW times XC plus, this is the removal rate. How much you can removing from the system is QW times XR. Okay. But the problem is, or not problem, to make it easier, X is equal to 0. The compared to, or another way to say is XR is very, very high compared to XC. Because your wastewater typically do not have lots of microorganisms. You remove them from the system. And your sludge has way, way higher the recycle. So that's why this equation become Vx divided by XW XR. So anytime somebody asks you to calculate how much sludge retains on time, or volatile suspended solid retains on time, or whatever the different they write different ways, SRT, then you will be able to calculate if you know the volume of the reactors and the concentration of microorganisms in the reactor divided by volume of waste that you are removing from the system and concentration of microorganism in that particular waste. So if you know these things, you should be able to calculate. But a lot of times SRT is given to you. It says 3 days or 5 days. And you have to calculate some other factors based on these particular equations. So you should just know everything by concept. I'm not solving any mass balance equation yet, because ultimately your final question answers will be you just plug these questions and get the value or answers. And so another way to write SRT is this way. This can be solved using mass balance equations. I am not solving today. I'm just saying that this exists. Okay, so just know the concept. So SRT is also depends on flow rate and all the other factors written here. KD is the death rate. This is the S0 is the amount of substrate that coming in minus the amount of substrate removing. So this means the difference in the change in concentration of BOD in the reactors. And Y is the yield, X is the concentration of microorganism, Q is the flow rate, and V is the volume of the reactors. Okay, so what it does, the second equation is very much important because you don't have to really measure the concentration of flow rate, this QW. You don't have to worry about the waste concentrations. If you don't know the waste concentration, which is most of the cases, you can still calculate SRT, because a lot of times the waste is not monitored. So that's why this is another indirect way to measure the SRT. So let's say there is a question, isn't that supposed to be QR in the denominators? I'm pretty sure let's see. Which one is QR? This is correct. If you see, this is the effluent. So these are all the effluents, okay? So I'm just writing the mass balance. This is all coming out of the system. So the flow rate is QW here. This is QW. So this is not QR.
Professor, I think he means below the picture and above where XR is a lot greater than XE. It should be QWXR.
QW. Oh, you are right. Writing twice. Thank you. A lot of typos. All right, so that's all you have to know. Another last concept is calculate the food to microorganism ratio. So food to microorganism ratio is basically how much food you have available for the microorganism divided by total amount of microorganism. So think of what is food means. Food means is total amount of BOD. So how much BOD you are supplying? S0. Okay. And how much BOD you supply, how much flow is coming in. So Q times S0 divided by total amount of microorganism. We just calculate total amount of microorganism Vx. So this is volume by this is concentrations of microorganism. Concentrations of microorganism. This is BOD or food. This is the flow coming in. Okay, so that unit would be, so when you think of the units of this one, this is Q over V will be time, 1 over time. This is a different unit. You cannot divide S0 by X as a different unit because they represent different things. This is milligram. So the unit will be milligram of BOD per liter divided by, this one is milligram of volatile suspended solid per liter. That's the unit of that. And then Q over B is over time. So let's say this is the unit. Okay. So what you are saying is amount of BOD is available per day per unit mass of microorganism. So that's the food per M. Why it is important? If you have more, if this is more, then it is more efficient because you have enough, um, you have enough you have enough food there for the treatments. But think of another thing. What will happen if this is less? If FM become less, that means your wastewater doesn't have lots of food. Okay, so that means you have to slow it down. If you have, let's say this one, you have lots of food per microorganism, you might not be efficient. So what you have to do is you have to recycle more. Okay, so that means your XQR should increase to make the efficiency, to make the wastewater more efficient. You will recycle a lot more because you want to maintain that certain food to mass ratio. So this is why this is a design variable. So that means these are usually fixed at certain rate. So you want to maintain that by varying your recycle rate as well as the wastewater flow into the system, because you cannot change the S value. S value you cannot change. That's like amount of BOD there. It's the quality of wastewater. You can vary Q or QR. These are your variables. So you can change those to maintain that food to mass ratio of certain value, optimum value. So that's all in terms of concept. Okay, so again, there are lots of factors, food to mass ratio. So you should know what that means. So read that textbook so that you know what those concepts really mean and why it is important. And these equations are given, so you just have to plug and value, get the answers. So what I'll do is, because it's 140 and I know that I can solve this one in 10 minutes. So I'm going to just to give it a try and say that how to solve these questions, because these are all basically plug the value, get the answers. The lot of times, this is not last year, this is 2018 final. Okay. A lot of times people have difficulty in these questions because they don't know what these different terms are. So 90% of the challenge is identifying those terms. Okay. So there is some question. If food to mass ratio, if it is high, it means efficient. If it is high, that means there could be two different things. It could be you have lots of contaminated wastewater. So your wastewater has a lot of pollution, a lot of pollutants, or a lot of BOD. And also it means that your this FMM ratio is applied to here. Okay, so F by M ratio is applied to aeration tank. You wanted to have a specific waste ratio for them to be efficient. So when your F by M ratio is high, that means you're lots of food for microorganisms. That means you have to recycle more. So your flaws recycle rates, you have to pump it up. All that means is that it's not about efficiency. If your food to mass ratio is less, that means you have way too much microorganism. You don't need that much microorganism. So what you can do is you can slow down your um, recycle rate. So food to mass ratio again is yes, you need certain ratio to be more efficient. It doesn't mean that you have to. Let me, in a second, let me make sure my sound doesn't shout. Pause. Okay, so let's read the question. I'm not going to solve completely, but your challenge is to find what different terms are. So a municipal wastewater treatment plant receives 3 million gallons per water per day. It says the amount of water received per day. That means you already know the Q is given. So I'm going to start writing those, okay? Q equal to 3 mgd. So this Q is given. And with average BOD concentrations, BOD is substrate, okay? So BOD 5 is 200 milligram per liter. So BOD 5 in substrate. So that means this is going to be S0 is 200 milligram per liter. That's what is coming in. Oh, I'm sorry. This is BOD. It's not S0. That's another thing to F influent. Because as I said, this is after the primary treatments. This is after the primary. So that's what it says. It uses the primary clarifier unit followed by a traditional activated sludge process to treat wastewater to maintain an effluent standard of BOD 10. So this is effluent standard. That means the BOD concentration. So it's talking about BOD. So that means S. A3 in the effluents should be around 10 milligram per liter. In the suspended solid concentration, so X suspended solid concentration is 15 milligram per liter. Anytime you hear suspended solid, you're talking about the microorganism, okay? Is 15 milligram per liter. So that means XC, this is, I'm just start going to write here, okay? So this is XE, this is SC, this is Q, this is again it's a BOD, so that means substrate. This is influent. I'm just writing influent. The reason is this is not after the primary treatments, so you have to assume how much primary treatment remove. Then it says that assume that 30% of the BOD is removed by primary clarifier. This is what I was talking about. So that means you have 200 milligram per liter BOD coming in wastewater. 30% are removed. So that means X S0 is 70% of what is coming in milligram per liter. So that will be 740 milligram per liter. I'm sorry, the noise is too much in the background. Then everything is given. So X0 is, did it says where the X0? All right, let's read and then we'll find out. The microorganism are 60% efficient at converting food to biomass. So what you're saying is the amount of biomass they produce, they are 60% efficient. So to converting food to biomass. So that's saying that how much biomass they produce per unit consumption of food. So if you think of the units of everything, where that units comes from here. So amount of biomass they produce per unit consumption of food. Okay, so they are 60% efficient. So yield is 0.0 Okay, so this is while yield equal to 0.6. The microorganisms, they have a first order death rate. So this is death rate is given. So the KD is given. And there is half of the maximum growth rate when the BOD concentration is 10. So again, what they're saying is there is half of their growth rate when the BOD concentration is 10. That means Ks, saturation constant. So this is Ks. Okay. Suspended solid were measured at 4,500 milligram per liters in wastewater samples obtained from the biological reactor. So that means if you measure the suspended solid, that's X here. So this is X. Biology reactors and 12,000 milligram per liter in secondary sludge and 240 milligram per liter in the plant influence. So here you are talking about X everything. Okay, so this is in from biological reactor. This is in secondary sludge, so that means X waste or XR, and then 240 milligram per liter in the plant influent. So this is XE. Okay, so you can write X equal to XW. Okay, so they are all very similar concentrations. 60% of the suspended solid in plant effluents are removed in primary clarifier. So it's saying that 60% of the suspended solids are removed in the primary clarifier. So let's see what does this mean. And remaining amount is fed to aeration basins. Then second thing is the sludge retention time is 5 days. So this is SRT. BOD decay coefficient is 0.2. So that's basically how quickly the BOD is being degraded. So that value is here, K. So that K is not here in the equations, but that degradation rate is basically BOD degradation, where that terms. It's not here. Okay, so that's BOD degradation rate. BOD degradation rate. So that means basically, if you remember, when we write the BOD concentration, BOD equal to BOD initials or in ultimate BOD times e to the minus KT. Okay, so this K is here. Okay, 0. This K is here. All right, so there are so many things given here. So it says calculate the volume of aeration basins. Everything else I already write it here. Volume of aeration basins. So volume, if you see, is here. There are two volume terms. So now you can solve for volume based on any of them, as long as everything is given. X is given. The only thing that's not given in that equation is QW. Anywhere, if you see, there is no QW. There is no amount of sludge produced per unit day. That's not given. So that means you cannot use these equations to calculate V. So that means if you use other equations, 1 over SRT equal to, I'm just going to write it there, QY by VX, QY by VX, S0 minus S, death rate times, okay, that's all. All right, so think of this way. So that means you can solve for V. Everything else is given. SRT is given, flow rate is given, yield is given because 0.6, X is given, we already write it there, S0 is given, S is given, KD is given. So you just have to calculate, solve for V. How many kilograms of secondary dry sludge need to be processed daily for the treatment plants? He's saying is how much amount of solid you are going to produce. So if you think of the equations that has amount of solid, is basically here. So this is amount of solid produced, because that's the waste. So if you see SRT equal to Bx QW X R. So I'm asking how much amount of solid needed process per daily is same as I'm asking QW XR times QW, because this is the total mass, concentration times flow rate. So I'm asking basically what is that value is. All right, so as you see, I try to solve it a little bit way. It's just the question on wastewater treatment plants are always messy in the sense that you have so many different terms, you have to identify them. Once you identify, you just plug the value in one of the question and get the answers. So there's really, it's not difficult in the sense that as long as you know what you are looking for, what these terms are, you can solve this question very effectively. All right, so that's all. I don't know whether this is the same questions or different questions. It's the same question, so there is no, this is not, it's just repeated. So that's all in terms of the wastewater. Again, this is not part of the midterms. I would suggest that read that 5 pages in the book. You should be able to understand everything what we cover today. Next class, what we are going to do is we are going to learn about different types of wastewater plant design, because I talk about just anaerobic here, aerobic here. I'm going to solve more questions on wastewater next class, as well as we talk about how to process the sludge, how to design wastewater in different types of design. Okay, so that's all for the class today. I'm going to stop the recording.